What was how much? For 10,000, total 10,000 there. I don't know what. Okay. Elements. There is a green arrow at the top. So, click on it. The green arrow there. So, break-even point is 666.1, 67. That revenue is what? 15,000. Actually, that's where all the that have been provided can be found. You see cascade, edit data. If you want to edit data, click on edit data. It will give you the interface to edit. If you want the break-even result, that's this one, click on it. This is the result now. If you want the graph, you click on graph of break-even analysis. That's one. So I click on it. The equivalent for Windows. No, didn't bring my car. Take that too. Come on. Okay. And price. Find the break even point. Is what? Sure. Right. On. So in Whatever problem and
solve it, both mathematically and also using the computer and also graphically. Because the graph is here, right? Mathematically, problem is what? I want to get the full meaning of the numerator and the denominator. Okay. So I hope when it comes to the exam, you will not forget. Instead of fixed cost, you say variable cost over jam everything. I think that you have had everything right. All right. Let's look at today's lecture. Programming. Linear programming. Mathematical through graphical solution. Let's read the computer solution. But for today, the focus will be on mathematical and graphical solution. And this has it. Okay. Don't say that it's not coming. Now, okay, about management science, there is always what we call the objective function. The objective function could either be a minimization function or what? A maximization function. Put another way, a linear problem could be a minimization problem or a maximization problem. Okay. Which the is linear. Two equations. You say something is linear, what does it mean? It what? Follows what? The pattern of a line, of a straight line. Okay. I have two equations on the board. Are you capturing this for those online? Hey, Muda, you have to be here. Okay? Otherwise, you'll end up blaming me. Okay? Now, equation 1, is it linear or nonlinear? Why? Okay, so if you plot this will be a straight line. So it's linear. Equation 2, is it linear or nonlinear? Is what? Why is it nonlinear? Because it has a polynomial. Okay, because of this quadratic term, it becomes a nonlinear. If you plot this, it will be a curve, not a straight line. So, it cannot be used to solve nonlinear equations. So, no. But this, yes. So, one of the most important things to note is to identify that this problem can be solved by linear program. If you go and pick for linear programming to solve, it will not fit. So that linearity is very critical when we are doing linear programming. Okay. 3 main steps involved in linear programming. Number 1 is to identify the problem as being solved by linear programming. And that's what I just illustrated. That when you see that there's a quadratic, a square, or a cube, the power other than 1, then we can use linear programming. Okay, so identify the problem as being capable of being solved by what? Linear programming. Number 2, formulate a mathematical model of the problem. State the problem mathematically. If you remember last week, I mentioned that in the management science process, the 5-stage process, the first 2 are the most important. The first step is what? First step is what? A. I'll use everything to ETZ. You have to reduce the TZ. Observation. The second step is what? Problem identification. The third is what? Model construction or formulation. The fourth is what? Model solution. And the last is what? Implementation. Okay. So, are able to identify the first 2. Now, observe the problem in real world. Number 2, identify what? The problem. Then number 3, formulate it mathematically. If you are able to do this, as for the solution, we said, by all means, we can solve it. If we can't solve it mathematically, we'll solve it what? Graphically. If we can't solve it graphically, we'll use what? Computer. So whatever the case may be, we will solve the problem. But the main issue is how to identify the problem and how to formulate the problem. And that is what we will do today. There are of a linear programming model. Number one is a decision variable, which determines the level of activity that the firm will undertake. So, for instance, how many bags of fertilizer to apply? That's the activity, and that's the decision. How many phones should the company produce to maximize profit? That's the decision variable. So in a linear programming problem, there is always at least one decision variable. Then objective function. Every firm has what? An objective. Either to minimize something bad or to maximize what? Something good. So therefore, we try to minimize cost, minimize loss, whilst we maximize what? Profit and revenue. Okay. Then we are living in a world of scarcity. Because of this, the decision maker is faced with constraints. If we were living in a world where resources were not limited, there will be no need for economics. The study of economics arose because resources are scarce relative to our needs. That's why in the Garden of Eden, there was no economics. Because everything is there. Whatever you want, you go for it. Okay, but since then, things have become scarce. So because they are scarce, we have to what? Manage resources very wisely. So there are always constraints that will restrict the availability of resources for maximizing profit or for minimizing what? Cost. Lastly, there are parameters. The parameters are known values to the firm or known values in the problem. When we were doing the cost revenue analysis, the break-even, we knew what? The fixed cost. So it's a parameter. We knew the variable cost. It's a parameter. We knew the revenue. It's a parameter. What we did not know is what? The volume. So the volume is a decision variable. Okay. You can, hello, just close it, but don't lock it. Close it, but don't lock it. No, it will, especially this one. This is fine. All right, thank you. So, must have decision variables, objective function, constraints, and what? Parameters. Let's look at an example. Now, it is very important for you to understand the story, because the linear programming problem will usually presented to you in the form of a story. That's where the first stage starts with observation. Observe the problem and identify it. Okay. So try to, when you are reading the problem, every word counts. Because if you misplace a word, you could have the wrong interpretation. And the wrong interpretation will lead to the wrong mathematical formulation. And once you don't formulate it well mathematically, obviously your solution will be wrong. Okay. So this is a firm that is called Beaver Creek Pottery Company. So what this company does is that it produces bowls and mugs. Bowls and mugs using two main resources: labor and clay. Two main resources, labor and what? Clay. Now, it has observed that to produce one bowl, you need 1 hour of labor, 4 pounds of clay, and when it sells the bowl, it will earn $40 profit. So we are trying to understand the problem, because if you don't understand the problem, you cannot set it up. It has also observed that if it wants to produce one mug, it will need 2 hours of labor and 3 pounds of clay, but it will get $50 profit for selling the one mug. So the decision that this producer wants to make is how many bowls and mugs to produce in order to what? Maximize what? Profit. Given constraints. So that's the decision. Now, let me show you the labor constraints. It has 40 hours of labor available per day. So it cannot get any labor hours more than 40. That's the maximum. It can only have 120 pounds of clay at its disposal. Nothing more than that. So that is what we call the resource availability constraints. So the firm is therefore required to maximize profit subject to what? Labor constraint and what? Constraints. Okay. So let's get back. Who doesn't understand the problem? Because if you don't understand the problem, when we solve it, you will not understand the solution. Yes.
The human itself for the house.
What do you mean? It's the human that is the labor, not so. Yes, it's the human being that is the labor. Yes, the labor is in hours. Hours. So take note of that, the units of measurement. Hours, not number of people. Okay. Yes.
At this way, where is the place that you'll be able to identify that they want to produce one quality of gold or one quality of mud?
No, it's provided here.
But I'm seeing
per unit.
Okay.
Per unit. Everything is measured on what? Per unit basis. Okay, and the unit is either a what? a mug or a what? A bowl. You understand that? Okay. So watch carefully how we formulate the problem. Now, we say that the objective, Buddha, you are blocking it. We said that the objective is to what? To do what? So, is to what? Maximize what? Profit, Z, which is equal to how much profit can we make from producing a bowl? How much? So 40, okay, this is how it starts. Let me not go ahead of myself. First, identify the decision variables. Okay, so let X1 be what? The number of what? Number of bowls to produce. Number of bowls to what? Produce. X2 is what? Number of marks to produce. It's very important to do that first. So, if we produce a bowl, we get how much profit? 40. So 40, and how many bowls are we to produce? We don't know. In order to maximize profit, remember. So that's why we said what? X1 plus profit from mark is how much? 50. How many marks will we produce? It's X. We don't know. So it's X2. So this is our objective function. So this is objective function. Subject to constraints. How many constraints do we have? We have what? From the problem we have 2. But I'll add a third one soon. Okay. Now, first is what? Labor constraint. What is the nature of the labor constraint? What is the maximum number of hours available? 40, not so. Means that the hours available for you to make bowls and what marks should not what? Exceed 40. Should be less than or what? Equal to 40. So, to be 4 1 as well. 2 x2 should be less than or equal to what? 40. That's the labor constraint. This is labor. This column is for what? Labor. 1 x1 plus 2 x2 is what? Less than or equal to what? 40. So that is our labor constraint. 1 x1 plus 2 what? Is less than or equal to what? 40. This is labor constraint. Now, let's look at the clay constraint. It will be what? 4 x1 plus what? X2 is equal to what? Less than or equal to what? 120. Because we have 120 of clay available. Why is your face like that? The 120 is here. Is that not it? It's part of the problem, not so. So for X1,
So where is the 120? We can see the 120.
X2 less than or equal to what? And this is the clay constraint or resource constraint. Where is the confusion coming from?
Away from the 120. Online, we can see the 120.
You can see the one.
Yes, the 120.
You can see the 120.
Yes, where is it coming from?
It's on the board.
That aspect is not showing.
Let me get your problem.
Okay, hold on.
The 120.
Thinking that the 40, no, the 40 is from the resource availability. Check it here.
The,
40
you
hours.
see,
Now,
the 40 is part of the table. The resource requirement.
To the
The
entire
120.
under constraint. The profit is not a constraint.
can you see now?
No, please. The 120.
No, it's on the
Where's-
slide. Check the slide
It's
there.
on the other side. Yes.
Those are the resource availability.
Check the slide here. The resource availability.
Okay. It's here. Yes. I've seen it. Thank you.
All right. So there is a last constraint. And the last constraint is that we cannot produce negative products. Okay? We can't produce negative board. We can't produce what? Negative mark. At least we can produce 0, but not negative. Okay? So this is how we write it. So X1, comma, X2 greater than or equal to 0. We call this non-negativity constraint. That one, we just need to state it to make the model complete. We don't do anything with it. Okay. Now, so this is the what we call the model construction. So we have constructed the model mathematically. Because after the solution, each one of you has their own method of solving this one, not so. So let's solve it. So call this 1, equation 1. Call this one, equation 2. So let's make S1 the subject in equation 1, not so. And when you are doing it, turn this inequality to an equality. When you are solving it, change this to an equality. This also to an equality. So that's how we solve it. So if we say we are making S1 the subject, so S1 will be equal to what? 40 minus what? 2x what? 2. So 40 minus 2x, we come and substitute it in what? Equation 2. Not so. So this will mean that so it will mean 4 times what? 40 minus 2x2 plus 3x2 is equal to what? 120. Four times 40 is what? 160 minus what? 8x2 plus what? So we now have what? 160 minus what? 5, 8x2 not so. Is equal to what? 120. It means that 5x2 is equal to what? 160 minus what? 120. We are just putting like terms together. So this is equal to what? 40. So 5x2 is equal to 40, which means that x2 is equal to what? 40 over 5, which is what? Which is equal to 8. It means that x2 is 8. Once we know that x2 is 8, we can substitute it in equation 1, not so. So from 1, x1 plus what? 2 times what? 8, not so. Is equal to what? 40, not so. X1 will then be equal to what? 2 times 8 is what? 16. We send it across. So 40 minus what? 16, which is equal to what? 24. The solution is that produce what? 24 books and what? 8 what? Marks. That is the solution. Produce 24 bulls and what? 8 marks. To gain a profit of what? To get the profit, come and substitute the values in the objective function. The 24 and the 8. So here we have what? 40 times what? Times what? 24 plus 50 times what? 8. And we'll get how much? Quick, with your calculators. $1,360. So we get what? 1,360, right? So this is the profit we'll make. Produce 24 bulls, 8 marks, and you get a maximum profit of what? 1,360. If you produce more than 24 bulls, you cannot get the maximum profit. If you produce less than 8, you will not get it. If you change any of these values, you will not get the maximum profit again. That's what the solution talks about. No, so we just solve it mathematically. But it is important for us to plot it in a graph. The alternative solution is to plot it in a graph. And I'm going to show you how to do that. So this one, I am not requiring you to ask for a graph sheet in the exam. Just a casual sketch. Okay, you don't need to bother yourself. So let's see how we get that done. Okay. Now, that's why I told you that identifying the problem and stating it mathematically is important, because every other solution we are going to come out with will be based on this. So now, to solve it graphically, we need to get the coordinates for the constraints, labor constraint and what? Clay constraint. The coordinates on a map. So let's get the coordinates for the labor constraint. How do we get it? First, we say that suppose x1 is equal to 0. That's in this equation. Suppose that x1 is equal to 0. What do we have? It will imply 2x2, because this will be 0, not 0, will be equal to what? 40. Which will mean that x2 is equal to what? 40 over what? 2, which is equal to what? 20. Which means that our first coordinate is what? 0, what? 20. 0, 20 for the labor constraint. So now let's say, now if x2 is equal to 0, it will imply that, so here we said x2 is equal to 0. So this will be 0, not so. So x1 will be equal to what? X1 will be equal to 40. You see, when we get the coordinates, first set one of the decision variables to be equal to 0. So we are saying that if x1 is equal to 0, that's this one. So it means that anywhere you see x1 here, put 0 there. So this becomes 0. So we now have our 2x2 is equal to 40. So you make x2 the subject, which will give you what? 40 divided by 2, which is what? 20. So you now say if x2 is equal to 0, so here x2 is 0. So x1 will be equal to 40, which is this. So that's our second coordinate. So the second coordinate will be what? This is x2. So it will be 40 what? Note the position. x1 is first, followed by what? x2. Don't change it. So it will be what? 40 what? 0. If we plot these points and draw a line, that will be the line for the labor constraint. I'll show you how to draw it very soon. So we are done with this one. We are left with this, the clay constraint. So we follow the same pattern. If x1 is equal to 0, that's for this one. So it will mean this is 0. This whole term for x1 is 0. So we now have 3 to be equal to what? F2 is equal to 120, which will imply x2 is equal to what? 120 divided by what? 3, which is what? 40. So we have another set of coordinates, which is what? 0, what? 0, 40. Now, if x2 is equal to 0, it will imply, so this one will be 0. This 0. So we will now have what? 4x1 is equal to what? 120. 4x1 is equal to 120. It will mean that x1 is equal to what? 120 over what? 4, which is what? 30. Which means that we have another coordinate, which is what? 30 what? 0. So we are also done with the Clay constraint. If we plot this on a graph, we'll get what? The Clay constraint. We are left with the objective function. Now, if you are going straight with the graph, you don't know that the answer to the objective function is 1,360. So you don't know z. So if we are going to use purely the graphical approach, assume any number for z. Any number. So let me assume that it is 900. That's my assumption. So I now want to find the coordinates for this one as well, z, which is the objective function. So if z is equal to 900, so if x1 is equal to 0, what will that be? 900 is equal to what? No, this is 0, not 3. So 50 x2, which will mean that x2 is equal to what? 900 over what? 50, which is what? 18. 18. So our first point is what? 0 what? 18. Now, if x2 is equal to 0, it will imply that 900 is equal to what? 40x1, because this is 0. 40x1. 40x1, which will mean that x1 is equal to what? 900 over what? 40, which is what? 22.5. So we have another coordinate, which is what? 22.5 what? 0. So we now have the coordinate set. We can graph. So let me clean this one for want of space. Yes. What's the question? Which number? I said any value. You can use any value. Yes. If you like negative numbers. Because if you assume negative, you are assuming that it's making a loss. You understand that? It will be the same. You arrive at the same conclusion. Okay. If you look at the coordinates, what is the maximum number for x? 40, right? That's x1. It's 40, right? What? This is not x. The first one is always x1. What is the maximum for x2? It's also 40. For the objective function, all of them are lower values. Okay, this is to guide me to determine how my graph will look like, the coordinates. Okay. So as I said, we are just going to sketch. I have 40, so I can just use 10, 20, 30, 40. So 10, 20, 30, 40,
When will
50.
you press that decimal?
So for this axis x1, sorry, this is what? X2. What do you say? 10, 20, 30, 40, 50. So x1, x2. So let's plot the coordinates. Let's start with the labor constraint. What were the coordinates? 0, 1. It means x1 is 0. So that's this point. This is a 0 point. 0, 20. X2 is 20. So I come and mark this. The second point is what? 40, 0. X1 is 40. X2 is 0. So that's this. So I connect these 2 points that I mark with the asterisks. It will be a straight line. So we label the labor constraint. Labor constraint. Let's look for the clay constraint. The coordinates are what? 0, 40. 0 for x1 and 40 for x2. And then the other one is what? 30, 0. So 30 and 0. So that's this point. So I connect them once again. Now, this is a maximization problem. We must find what we call the feasible region. This is the region where our solution is mathematically possible. The feasible region is the area below the intersection of the two curves. See where they intersect. This is the intersection. Now, if our graph is well structured, if we trace this down, this is supposed to be our one. We found x1 to be what? 24. Remember, 24. The number of volts to produce. Then we found x2 to be what? 8. If we trace it well, and the graph is correct, this is how it's supposed to be. At the intersection. The feasible solution, as I said, is the region below the intersection. So this is, so let me shape the feasible area. So this is called the feasible region. So in order to show it clearly, I delete all these points that are not pi. So we now have a curve of this nature. In linear programming, the optimal solution is a corner solution. How many corners do we have in the diagram? How many corners do we have? We have 4 corners. We have 0, 0, 0, 20, 8, 24, or 24, 8. Then we have what? 0, what? 30. But usually this 0, 0, we don't consider that. Because if you produce 0 mass and 0 booms, you get 0 profit. So it's out. We want to do business. Okay? So the points that are then considered are these 3. One of them is the optimum point. So A, B, and what? C. If we had not solved it mathematically, we would not have known that it is what? B. But how to know that it is B is to plot the coordinate for the objective function, which we found to be this. So we said 0, 18. So that will be here, right? And then we have 0 at 22.5. So 22.5 will be somewhere here. So we join the 2 points. So it's supposed to be a straight line. That is the line for the objective function. Now, the graph to determine which of the points is optimal. This is the question you ask. If we hold the line in its dimensions, and we are going to take the line out of this space, which of the 3 points will it touch last before exiting? Is it point A, point B, or point C? Maintaining the structure of the line. Which place do you think it will touch last? It cannot be A. To a B. Okay, if you do it, you see that the next line will be here. We have already crossed A. Then you now come next one. Next one. Then next one. So B will be the last point we attach before we exit. So that's the last point the objective function will touch before exiting the area. So graphically, we know the answer is B. So we can also get a solution that way. If you are still not sure, what you do is that use the coordinates. This point is what? Is what? 0, 1, 20. This point is what? 24 or what? 8. And this point is what? 30 what? 0. So our objective function is equal to what? Is 40x1, right? Plus what? So you can plug this in here to get the profit. Plug this in to get the profit. Plug this in to get the profit. The one with the highest profit is the solution. And you see that all of them will arrive at B. Whether we use the graph, we use the mass, it will settle on what? B as the solution. Okay. So this is how you solve a simple linear problem. It's a simple linear problem. Because suppose that we have 4 decision variables. So it is producing mass, it is producing caps, and some other souvenirs are added. That would be more than 2 decision variables. So we usually say that more than 2 decision variables, we use computer software. But 2 decision variables, that one you can solve it on your own. That's why I said this is a simple problem. Now, we have what we call slack variables. Let's look at the constraint. I'm coming. The first constraint is what? X1 plus what? 2x2 is what? Who was asking the question? What was the question? No, it will not change. It will not change. You'll just be viewing the graph from the other side. So if you want in your book, you can change it like that. To do the same. Now, we know that x1 is what? What is the value of x1? 24 plus x2 is what? is less than or equal to what? 40. 24, 2 times what? 16 is less than or equal to what? 40. 24 plus 16. 40 is what? Equal to 40. It can no longer be less than or equal to. It's now equal to what? 40. Let's go to the second one. We said 4x1. So x1 is what? 24 plus
3.
3 times what? 8. Not so. It's equal to what?
Less than or equal to
120. 4 times 24 is what? 96 plus what?
24.
24 less than or equal to what? 120. So 96 plus 24 is what? So 120 is what? Now, what this means is that we do not have surplus resources. Or we are using all the clay and all the labor hours available. The resources are used to maximum. In that case, we say that there is no slack. A slack variable is a value that we need to add to the constraint in order to turn it into an equality. So for example, if you take equation 1, if we were to use only 35 of the labor hours available, we'll have 35 less than or equal to what? 40. And the surplus will be what? We call that slack variable. That is an unused resource. So we call it a slack variable. Now, these constraints are all satisfied with equality. See that 40 is equal to 40, 120 is equal to what? 120. We say that the two constraints are binding. Binding constraints. A constraint is either binding or what? Is non-binding. Where the constraint is binding, it means that the constraint is satisfied with equality. So that if you are not able to utilize the 40 hours of labor and then the 120 pounds of clay, you cannot get the maximum profit. And the constraints will lead to you not achieving your objective of $1,360 of profit. Let me learn first. I know I have to get somewhere. Should be patient. If, however, we found that there is a slack greater than 1 or greater than 0, then we say that the constraint is what? Non-binding. So if after solving the problem I ask you, determine which of the two constraints is binding, you know what to do now. Or you know what to do. You cannot just say, oh, this one is binding now, but you have to show working. Okay. So that's the essence of what we are doing. Now the question.
So, Allah, you can mute them. And I think Salma also wanted to ask a question. Go ahead.
Yes, it has to do with the Slack. Started with the Slack is a variable that you need to add it to a variable that will give you that will turn into the equity this thing. I didn't get that part right. So as you keep moving, escaped. I didn't get that part right. You're saying a Slack variable is a variable you need to add into something to turn it into equality, equity.
Yes, so you really didn't understand what that means.
Yes, I didn't get it. So as he was moving, it skipped. So I wanted to really get it and follow.
Okay. So probably asking that when you said the Slack variable is a variable that you add to make it equal, right? What do you mean by that?
Okay, that's fine. So,
Thank you.
for instance, okay, beautiful. So, if you are going to write the first constraint, this is the first constraint, right? So I'm going to add a slack. S1, call it S1. So I can no longer say less than or equal to. It has to be what? Equal to what? 40. Because anything that is short for the left-hand side to equate to the right-hand side will be made up by what? S, which is a slack. The slack can be any value. And in the example we give, the slack is equal to what? It's 0.
Yes.
The two examples, the slack is equal to what? 0. Because 40 was equal to what? 40, 120 equal to what? 120. So there's no slack. It's 0. The same for the second constraint. So the slack, as I said, is the value that has to be added to the constraint to turn it from an inequality to what? Equality. The slack does nothing to the objective function. Okay? It doesn't change the objective. When you are adding the slack to the objective function, so for instance, the objective function we have, we say G is equal to what? 40 what? X1 plus what? 50 X2. We have two slack variables, X1. So this is how you add it. Plus 0 S1. Plus 0 what? S2. Because the slack does not affect the objective function. It only affects what? The constraints. And the constraints are first stated with what? Inequality. But you use the slack to convert them to what? Equality. Now, so there are several ways I can require things of you. So you can solve the problem and I'll ask you, is there slack? You cannot just say yes and run away. You have to stay there and solve the problem. Okay, so show whether there's slack or what or not. Okay, so take note of that as well.
So I hope your question is answered.
Yes, sir. Thank you.
Welcome.
Let's look at
Sorry.
minimization problem. What we did was maximization. So minimization is just the other side of the coin. So if you have a coin, just toss it. One face, head, the other one tail. It's just the opposite. Okay. So let's look at a typical minimization problem which you should be able to solve. So look at the information on the board. Here we are dealing with a farmer who has a problem. And his problem is not about food, but fertilizer. His problem is there are two brands of fertilizer that he's interested in. Supergrow and CropQuick. They have different prices. Supergrow costs $6 per bag. CropQuick costs $3 per bag. His land requires at least 16 pounds of nitrogen, 24 pounds of phosphate. Now, what he wants you to help him to do as an expert, he cannot do it. It's not as educated as you. You are his consultant. So he tells you, given this information, I want to know how many bags of Supergrow and CropQuick I should buy so that I can minimize cost. Now his problem is minimizing cost. He doesn't know about profit yet. And this is additional information provided in terms of the chemical composition of the fertilizers. If you take Supergrow, each bag contains 2 pounds of nitrogen and then 4 pounds of what? Phosphate. CropQuick, each contains 4 pounds of nitrogen and then 3 pounds of what? Phosphate. So he wants to know how many bags of Supergrow, how many bags of CropQuick he should buy so that he will what? Minimize cost. So first, let's identify the decision variables. So X1 is what? Number of what? Number of bags of what? Bags of what? Supergrow to buy. X2 is what? Number of bags of what? CropQuick to buy. If you are able to identify this variable, then you have solved a problem. That's really where the problem is. Okay, but if you cannot identify which one is X1, X2, then you can't solve it. So first, let's find out what is the objective function. What is the objective? Minimize what? So we are minimizing cost Z. And it's equal to what? 6 what? A bag of super glue costs what? $6. 6, so 6x1 plus what? 3 what? X2. That's the objective function. Are you with us? Now, this cost is minimized subject to nitrogen constraint and what? Phosphate constraints. Because the field requires at least. That word at least is not there for nothing. It means something. There's a mathematical meaning to it. It means that it can be what? More than 16, but not less than. The same as the 24. Can be more, but not less. So that changes the way we formulate the what? The minimization problem. In the maximization problem, we're using less than or what? Equal to. But this one, we have to use greater than or equal to. So let's formulate the phosphate, the nitrogen constraint. What would be the nitrogen constraint? To be what? 2 what? 2x1, that's from here. Look at it from here. 2x1 plus 4x2 is equal to 16. Greater than or equal to 16. Then the phosphate one will be what? 4x1 plus what? 3x2 is greater than or equal to what? 24. Are we together? So 2x1 plus 4 what? X2 is greater than or equal to what? 16. This is the phosphate constraint. Phosphate, I'm going to shorten the phosphate constraint. Sorry, nitrogen, sorry. You are monitoring the process, pan. I'm happy about that. Then you can now have the phosphate constraint, which is what? 4x1 plus 3x2 is greater than or equal to what? 24. So this is the phosphate what? Constraint. We are left with our last constraint, which is what? The non-negativity constraint. Don't forget about it. So that one is what? S1, comma, S2 greater than or equal to what? 0. So this is a complete mathematical construction of the model. Once again, once we get here, up for the solution, we'll get it. Whether mathematically, graphically, or what, computationally, we'll get it. Okay? But look at it this way. Here, we are trying to minimize. Because we are trying to minimize, unlike the maximization constraint, where we can just say this is equal to 16, this is equal to 24, and then we solve for x1 and x2, and we say that that's the answer. Here is not the case. Here, when you find x1 and x2, they will be the intersection points, one of the solution points. So you have to find x1 and x2, then you have to find all the corner points. Remember, in the maximization case, we plotted and got what? 3 corner points, A, B, and C. Here again, we'll do a similar thing. The same process. Okay. So let's start with getting the coordinates for the graph. So if x1 is equal to 0, it will imply what? Let's deal with the nitrogen first. It will be what? 4x2 will be equal to what? Which will imply that x2 is equal to what? 16 over what? 4. X2 is equal to what? So our first coordinates will be what? 0, 4. If x2 is equal to 0, it will imply that from here, 2x1 will be equal to what? Which will imply that x1 is equal to what? 16 over what? Which is equal to what? 8. So our second coordinates will be what? 8, 0. So this, if we plot this, we'll get the line for the nitrogen constraint. Let's go to the second one, the phosphate constraint. If x1 is equal to 0, it will imply that 3x2 will be equal to what? 24, which will imply that x2 is equal to 24 over what? Which is what? 8. So our first coordinate here will be what? 0, 8. We have 8, 0. We now have what? 0, 8. If x2 is equal to 0, it will imply that for x1 will be equal to what? 24, which will imply that x1 is equal to 24 over 4, which is what? 6. So our third coordinate will be what? 6 and then 0. So this can give us, this is the nitrogen, this is the what?
Okay.
The phosphate constraint. Let's go to the objective function. We want to minimize cost. Now we don't know Z. Remember, in the course of the maximization, we said we can assume any number, not so. So here we can assume any number. Are you expecting a negative cost? Is it reasonable? Okay? So you have to think critically about it. It's not about, oh, let's use negative. But look at the problem you are dealing with. So let's say it's 21. Let's say z is equal to 21. I'm just guessing. Okay, so it will mean that if x1 is equal to 0, it will mean 21 is equal to what? 3x2, which will imply that x2 is equal to what? 21 over what? 3, which is what? So our coordinates will be what? 0, 7. If x2 is equal to 0, it will imply that 21 is equal to what? 6x1, which will imply that x1 is equal to what? 21 over what? 6, which is what? What? 3.5. So our last coordinate will be what? 3.5 and 0. So and now plot these points to get the corners. And once again, with linear programming, the optimal solution is always a corner solution. Okay, so we will get 3 corners from what we have done. Okay, so let me clear here. From the values, I think the largest number we have seen is what? 8. So we can just do 1, 2, 3, 4, 5, 6, 7, 8. All right. So this is x1, this is x2. Let's plot for the nitrogen. We have 0 what? 0, 4. So we are here. Then we have what? 8 what? 0. 8 and 0. So that's here. So we connect them. So this is our nitrogen constraint. So you can label this nitrogen constraint. We now have to come to the phosphate constraint. And we got what? 0 what? 8. 0, 8. Then 6 what? 0. Now, these are the intersection, these are the corners. In the minimization problem, the feasible solution lies outside of the intersection. Unlike the maximization, where the feasible solution is below the what intersection and the corner points. So our answer is either this point, which is what? 0, 1, 0, 1, 8, or this point, which is what? So C, which is 8, 0. Or here, we don't know here. We have to find it. Especially because we are sketching, we cannot tell exactly what this is. We have to find it. So let's get back to our equations. The labor constraint, we said is what? 2x1, the nitrogen constraint. So we have 2x1 plus 4x2 so right now we state it as an equality. Then the second constraint, which is what? Call this equation 1, call this equation 2. So right now we want to solve them simultaneously. So there are several ways of solving it. You can choose your mathematical solution. But one of the easiest is to multiply equation 2 by what? 2. So that you can get this one also becoming 4. Okay. So multiply equation 1 by 2. So 1 times 2 will now be what? We have what? 4x1 plus what? 8x2 is equal to what? 32. So call this equation 3. So let's do equation 3 minus 2. So 3 minus 2. 4x1 minus 4x1 is what? 0. So that one, 0. 8x2 minus 3x2 is what? So 5x2 is equal to 32 minus 24 is 8. So it will imply that x2 is equal to what? 8 over 5, which is what? 1.6. Now we know that x2 is what? 1.6. We substitute x2 in equation 2 to get x1. So substituting x2 is equal to 1.6 in equation 2 will mean that we'll have what? 4x1 plus what? 3 by what? Is equal to what? So 4x1 is equal to 24 minus 4.8. So x1 will then be equal to what? 19 point what? 2 divided by what? 4. So S1 will be what? 4.8. So it means that at the intersection point, the coordinates are S1 is what? 4.8, and then S2 is what? 1.6. So that is point B. So this is supposed to be 4.8. And this is supposed to be 1.6. We almost got it, even with the sketch. Yes, you get it. Exactly. But approximately we are there. Okay. So look at it this way. This point B is 4.8, and then what? 1.6. Let's plot the line for the, I think we did for the objective function, right?
Yes.
Or we've not done it. Okay, let's do it. We did it. We did it. That's this one. Yes. So it's the plotting I wanted us to do. So we got what? 0.7 and what? 3.50. So 0.7. 0. And then what? So look at it. The solution is either point A, point B, or what? Point C. Now, you ask yourself a similar question as we asked. Remember, this is the objective function line. If we want to move this line, maintaining its shape and coordinates, and move it out, which of the points will it touch first before it exits? Which of the points will it touch first? Not last, first. This one is a minimization, so we are looking for the smallest cost. So we are looking for a cost that is closest to the origin. We would have been happy if the cost is 0. Planting for food. But we cannot get it. Okay, so we look for the one that will be the least. So will it be A, B, or C? To be A. If you are going to use this objective function line, the first line it will touch when it is leaving is what? A. So the solution is buy 0 bags of what? Super glue and 8 bags of what? Crop quick. So that's the advice we are giving to the farmer. We are saying that run away from super glue. It is too expensive. Buy and buy bags. and it will minimize your cost for you. Now, if you were to be unsure whether point A, B, or C is the correct answer, substitute these values in the objective function and get the cost. So substitute, where is our objective function? So Z is equal to what? So let's start with point A. X1 is what? So 6 times 0 plus what? 3 times what? 8. It will be what? 24. So at point A, Z is equal to what? 24. Let's move to point B. Z is equal to what? 6 times what? 4.8 plus 3 times what? 1.6. Z will be equal to what? Just do the multiplication and summation. 33.1.6. So at point B, Z is 33.6. Let's go to point C, the last point. At point C, Z will be equal to 6 times what? 8 plus what? 3 what? 0, which is equal to what? 48. So at point C, Z is equal to what? So 24 cost, total cost, 33.6 total cost, and then 48 total cost. Which one is smaller? 24. So it agrees with the fact that the answer is in what? Point A. So that's how you solve it mathematically and what? Graphically. Next week, we are going to learn how to solve it using the computer. So for these problems, it's already done now. So for these calculations, practice them. Because or not, you will see it in the, you will see something like this in the exam. This one, there is no two ways about it. So get you to read now. So that you will not suffer later. The work with the whites. Mm. Okay.